In our last unit for Unit 5, we talked about the extreme value theorem first. Remember how we talked about in order for there to be an absolute minimum and an absolute maximum, it has to be a closed interval, and it has to be continuous on the closed interval. So because this is not a closed interval, there is no absolute minimum. There is an absolute maximum, just no minimum because of that. On this next one, it did happen to be a closed interval at the endpoints. So this is the absolute minimum, this is the absolute maximum, and then here we have a relative minimum, just not the absolute minimum. On this one, because it was not a continuous function, it was not continuous at 0, therefore there is no absolute maximum. There was an absolute minimum and a relative minimum here, but just no absolute maximum because of that discontinuity. So on and so forth. So this one has no minimum or maximum because it's infinite. It goes down forever and up forever, so that's why it didn't have a maximum or a minimum. So extreme value theorem, in its essence, essentially said that in order for there to be guaranteed to be an absolute maximum and minimum, that it has to be a closed interval and it has to be continuous throughout the entire interval. There were times that we were asked to find, I don't know if there's any in this PowerPoint. No, there weren't. There were times that we were asked to find the absolute maximum and minimum. In that case, you would analyze not only the endpoints to see, like plugging in the endpoints to the original function to see if how high or low they were, what their y values were, but then in addition to that, also looking at the critical points in the interval. So finding the derivative, setting it equal to 0, and then taking all those x values and plugging them back into the original function to figure out what their y values were. You could create like a little xy chart to organize everything and then look at the highest point and the lowest point in order to figure out the absolute minimum and the absolute maximum in that interval. After that, we talked pretty at length about function analysis and talking about when a function is increasing, its derivative is positive since it has positive slopes. When a function is decreasing, its derivative is negative. Whenever a function's derivative is equal to 0, or if it's undefined, we call that a critical point. The relative or local minima or maxima would be the critical points that are changing from positive to negative for maxima and minima from negative to positive. We pretty much filled out this whole worksheet. We started creating this chart, which you do not get to use on your final, but I would definitely go through again, make sure you're clear on how these things relate to each other. So remember that increasing relates to a positive derivative because the slopes are positive, decreasing relates to a negative derivative because the slopes are negative, so on and so forth. We answered some of those questions. You can go back and look at those later. Then we talked about concavity. So we said concavity talks about the shape of the graph. If a function's increasing at an increasing rate or decreasing at a decreasing rate, we call that concave up. And the tangent lines lie below the curve in this example. So here's a function that's concave up and it's increasing. Notice that the slopes are getting steeper. So this is increasing at an increasing rate. And then here the slopes are getting steeper as well because they're getting less negative. So this is decreasing at a decreasing rate. So the slopes are getting less and less negative, so concave up as well. The opposites were true for concave down. And then we started to come up with these relationships between functions and their derivatives. So if a function is concave up, then its first derivative would be increasing because the slopes are increasing. And its second derivative would be positive because if the first derivative is increasing, then the slopes of this function must be positive. So its derivative had positive values. So concave up relates to increasing, relates to positive. Concave down is decreasing on the derivative, which is negative on the second derivative for similar opposite examples, but similar reasons. Go through and read through these notes again. These should be really helpful in understanding the relationship. Make sure, again, that you go back and look at this table in its entirety and really commit that to memory. After that, we talked about the mean value theorem. We said that a function, you can make the tangent line, which is this black line, be parallel to the orange one. So the tangent line can be parallel to the secant line, meaning that they have the same slopes, at least one point in the interval, as long as the function is continuous and differentiable. So here was an example where that wasn't possible. Because this function is not differentiable, because it has that cusp, then we could not make this black line parallel to that orange line anywhere in that interval because of that. Here, however, same function, but we changed the interval, so as long as it's differentiable over the interval you're looking at, then it will be possible to make the tangent lines and secant lines equal to each other. This one was not continuous, so remember it has to be continuous and differentiable in order to make those lines parallel. And then here was the mean value theorem we wrote down. So there were times when we were asked to find like a c value that made this true. So if you can find the slope between the endpoints for the average rate of change, then you can take the derivative and set the derivative equal to that slope and solve for whatever x value made that true so that you can figure out the c value that forced the mean value theorem to be true. And the last thing we talked about in this unit was local linearity. We said that a function can be very curvy, but as soon as you look at a tangent line at one point, as you get closer and closer and closer to that point, the tangent line starts to become more and more accurate to what the function's values actually are. So notice that when I zoom into this function and I keep bringing these points closer and closer, notice that these 2 points are getting very close to each other the closer and closer I get to the point of tangency. So we call that local linear approximation using the tangent line. And we did some examples of it in class where we were asked to write the equation of a tangent line, and then once we knew the equation of the tangent line, we were supposed to plug in this point, negative 1.01 or whatever it was, plug it in, and then go ahead and approximate what the value of the function is using the tangent line approximation. So that was the last lesson that we did. So now we're going to take some time. We're going to go over to our packet, and let's go ahead and look at the last answers in our packet to make sure that we're all good to go. So let's start with number 4. Number 4 says, here's a second derivative. Let's see if me turning off this light helps. A little bit, maybe. Here's a second derivative. It says, then the graph of f is concave up for blank. So remember, concave up, if I'm looking at the second derivative, a function is concave up wherever the second derivative is positive. So because they're giving me the second derivative, all I have to do is graph that function. I know I have a 0 at 0, and I have a 0 at negative 2. I know the 0 at 0 is a cross. I know the 0 at negative 2 is a bounce because it's multiplicity 2. If I look at all the x's, there are 3 x's, which means this is a cubic function. So at negative 2, this function will bounce, and at 0, this function will cross through. So it looks something like that. So if I'm looking for where the function is concave up, I want to know where its second derivative is positive. So anywhere that x is greater than 0, we have a positive second derivative, which means I'm looking at answer choice B. All right, there's number 4. The next one I want to look at is number 10. On number 10, they're telling us that this is a graph of f, and they want to know which of the following could be a graph of the derivative f prime. So let's look at the slopes first. So between here and here, which looks like it's at about 2, in between 0 and 2, the slopes are negative because the function is decreasing. And then after 2, between 2 and 4, the slopes are positive because the first original function is increasing. So I'm looking for a graph that starts off as negative and then changes to positive. So answer choice C or D could be those values. A is not ever negative, B is not ever negative. E, can't see E on my screen. E starts off being negative but then changes to positive and goes back to negative. So it could not be A or B or E. So now at this point, we're just trying to decide between C and D. And I might look at a couple different things. I think I'm going to look at the concavity. So if you notice right here, the function's concave down. So I'll kind of highlight. The function's concave down there, and it's also concave down there. So look at the shape of those two pieces. From here to here, it's concave down like a frown, and then over here as well, concave down like a frown. In between those 2 points, however, it's concave up like a cup. So notice that it changes concavity 2 times, and it starts with concave down, changes to concave up, goes back to concave down. If I'm thinking about the derivative, that means the derivative would change from decreasing to increasing back to decreasing again, because the second derivative would be negative to positive to negative. So of these 2 options, D is the one that starts with decreasing, then back to increasing, and then back to decreasing again, whereas C is increasing the whole time. Since this function is increasing the whole time, its original function would have always been concave up. That means D is the only correct answer choice here. The next one we'll look at is number 12. Number 12 says, the function f is defined by f of x equals that cubic function. The application of the mean value theorem to f on the interval from 1 to 3 guarantees the existence of a value c, where 1 is less than c is less than 3, such that f prime of c equals blank. So remember, the mean value theorem says the slope of the tangent line, which is f prime of c, must be equal to the slope of the secant line, f of b minus f of a over b minus a. So if I can essentially figure out what the slope of the secant line is, that would be the answer to this question. The slope of the tangent line must be equal to the slope of the secant line. So I know that my b and my a are 3 and 1. If I plug them into the original function, if I plug in 1, I get 2 minus 4 plus 1, which is negative 2 plus 1. Negative 2 plus 1 is negative 1. So when I plug in 1, I get negative 1. When I plug in 3, I get 3 cubed is 27. 27 times 2 is 54. Make some notes over here. 54 minus, if I plug in 3 here, I get 3 squared is 9. 9 times 4 is 36. And then plus 1. So we have 55 minus 36 essentially. And when we subtract 55 and 36, we get 19. So we plug in 19 here. So I have my 2 points. If I want to know what f of b minus f of a is, that would be 19 minus a negative 1 over 3 minus 1, which is 20 over 2, and 20 over 2 is 10. So therefore, the average rate of change is 10. Therefore, the instantaneous rate of change, f prime of c, must also be equal to 10. That's number 12. For number 13, it says, let f be a function with its derivative given by this. At which of the following values of x does the graph of f have a point of inflection? Now remember that points of inflection are most easily determined from the second derivative. So since this is the first derivative, I'm going to go ahead and find the second derivative. F double prime of x is equal to 3x squared minus 4. And remember that a point of inflection is wherever the second derivative is equal to 0 and changes sign. So if I set this equal to 0, I would get that 3x squared equals 4, x squared equals 4/3, and then take the square root, x equals plus or minus the square root of 4/3. Now, I don't see that as a specific answer, but if I take the square root of 4, I get plus or minus 2 over radical 3, and that is one of my answers, answer choice C. Notice that it did not include both of them, the positives and negatives, but it didn't ask for both of them. It just said which of these could be a point of inflection. So 2 over radical 3 is the only one that could be a point of inflection. All right, that's number 13. Next, let's look at 21. Number 21 says the function has a first derivative given by that function. At what values of x does f have a relative maximum? So if I look at this function and I graph it, first of all, I have 1, 2, 3, 4 x's. That means it's a quartic function. So I have a 0 at 0, a 0 at 3, and a 0 at negative 1. And it's going to bounce at 3 because of the squared. So I come down and I cross through at negative 1, cross at 0, bounce at 3, looks like that. It says, at which of the following values of x does f have a relative maximum? So a maximum is a 0 of the derivative that changes from positive to negative. So negative 1 is a relative maximum. Answer choice A. 0 is a minimum and 3 is neither. So that's why we're not choosing those. All right, that's number 21. 26. For what values of x does the graph have a point of inflection? So again, I have the original function. To find a point of inflection, it would be helpful to have the second derivative. So y prime is equal to 15x to the 4th plus 40x cubed, and y double prime is equal to 60x to the 3rd plus 120x squared. So if I want to know where this has a point of inflection, I want to know where the second derivative is equal to 0 and changes sign. Now, I can take out a GCF here of 60x squared. If I do that, I get 60x squared times x plus 2 equals 0. 60x squared is not going to give me a point of inflection because I have a 0 at 0, but it bounces because of the squared. So that's not going to be a point of inflection. X plus 2, however, is going to give me a point of inflection at negative 2. So B is the correct answer choice here. All right, number 28. For number 28, it says let f be the function defined by this cubic function on which of the following intervals is the graph of f both decreasing and concave up. So to be decreasing, I'm looking for where the first derivative is negative. And to be concave up, I'm looking for where the second derivative is positive. So I'm actually going to create a sign chart for this, and kind of like what we did with straight line motion. So I'll try to do my best over here. So let me take the first derivative. F prime, I might actually need a second sheet of paper. There's not a lot of room here. So f prime of x is equal to 6x squared minus 6x minus 12. If I want to know where that's equal to 0, I can divide everything by 6. That's x squared minus x minus 2 is equal to 0. This factors to x minus 2x plus 1. So that means I have critical points at x equals 2 and x equals negative 1. Now for the second derivative, move this over. F double prime of x is equal to, from the derivative of this first function, we would get 12x minus 6, and I want to know where that's equal to 0. If I divide everything by 6, I get 2x minus 1 equals 0, therefore x is equal to 1/2. So I have a critical point of the first derivative at 2 and negative 1. I have a critical point of the second derivative at 1/2. If I go ahead and graph these points, we have negative 1, 1/2, and 2. Kind of like how we did with the straight line motion. We can divide up our graph that way. Now, if I think about this first function, if I think about the first derivative, I'm going to put all the first derivative signs on the top and all the second derivative signs on the bottom. So for the first original function at 2 and negative 1, I'm going to have a quadratic function with a positive orientation. So I know that this function starts off positive, changes to be negative, and then goes back to being positive again. So on my sign chart, when x is less than negative 1, it's positive. In between negative 1 and 2, we have negative values. And then when it's greater than 2, we have positive values again. And then with the second derivative, this is a straight line with an x-intercept of 1/2 and it has a positive orientation, so it looks like this. When x is less than 1/2, the values are negative. When x is greater than 1/2, the values are positive. So we have negative values, positive values, positive values. So going back, let me fold this over really quick. Going back to our notes from earlier, I'm looking for where the first derivative is negative and the second derivative is positive. So if I look at this sign chart, the first derivative is negative here and the second derivative is positive here. So if I highlight, then those two are going to overlap right here. So this is where the first derivative is negative and the second derivative is positive, which means the original function is decreasing, that's because of the negative, and concave up, that's because of the positive. So in between 1/2 and 2, I'm looking at that the function is decreasing and concave up between 1/2 and 2. So that would be answer choice D. And that's number 28. The next one we need to look at is, we skipped one in the previous video, so we'll come back to it now. I accidentally skipped over it. It says the function p of t models the population of the world in billions of people, where t is the number of years since January 1st, 2010. Which of the following is the best interpretation of the statement p prime of 1 equals 0.076? Well, there's a lot of moving pieces in this problem, but I think one of the first things that's important to note is that p prime is an instantaneous rate of change. Since this is a derivative, we're talking about an instantaneous rate of change. So this is happening at one instant in time. So let's just first look at these dates. This is saying at a specific date, at a specific date, at a specific date. And then down here, we're talking about a range, like from January 1st, 2010 to January 1st, 2011. That looks like an average rate of change, something changing over time, whereas p prime, being a derivative, means something's changing instantaneously. So I'm going to go ahead and say D isn't quite what we want it to be. This one, when the population of the world was 1 billion people, the population of the world was increasing at a rate of 0.076. Well, this number in here, 1 does not represent the population of the world. This is a time value. This is p of t. So I'm not talking about when the population was 1 billion. I'm saying at some specific time, the rate of population changing was 0.076. So I'm going to go ahead and say E doesn't sound right. So let's look at A, B, and C now. This first one is the only one with the unique date. B and C both have the same date. So this is talking about February 1st, and these are both talking about January 1st, 2011 versus February 1st, 2010. So if we look at T, T says the number of years. So P prime of 1 would be after 1 year. So if it starts on January 1st, 2010, then after 1 year would be January 1st, 2011. So A is out. All right, so we've narrowed it down to two different contexts. The first one says that the population of the world was increasing at a rate of 0.076 billion people per year. And the second one says the population of the world was 0.076 billion people per year, or billion people, excuse me. Now, because this is a derivative, remember that derivatives are rates. It's how quickly something is changing. We talked about that when we talked about related rates. So because of that, because this is how quickly something is changing, it needs to be how quickly something is changing over time, billion people per year. I'm liking that. It's not a value. It's not 0.076 billion people. It's how quickly the population is changing at that time. So B is the correct answer for number 1. All right, number 5. We have ventured into the calculator section. So let me go ahead and pull out my calculator. We'll talk about this one. So it says the first derivative of the function f is given by f prime of x equals sine of x squared. So I'm going to go ahead and type that in. Sine of x squared, which looks like this. It says, at which of the following values of x does f have a local minimum? So I'm going to go ahead and look at my window, just make sure it looks good. I don't see any negative values in my answers. It goes from 2.5 down to 0. So I'm just going to go from maybe -1 up to 3, just so I can make sure to include everything. Now I'm looking for a local minimum, so I really don't need from -10 to 10. I just need where it's crossing the x-axis. So I'm going to change it from -3 to 3. I'm just trying to zoom in on that x-axis and kind of see what's happening there. All right, so it says the first derivative of the function is given by this equation. This is a graph of the first derivative. At which of the following values of x does f have a local minimum? So if we look here, the graph starts by increasing and then goes to decreasing. Here it crosses through the x-axis as a maximum, and then here it comes back up and crosses through the x-axis as a minimum. So this is where the function has a local minimum. Now if I'm looking at x values to try and figure out from the graph what that looks like, this is x equals 1, x equals 2, and then x equals 3. So I'm guessing this is about 2.5. So if I'm looking at my answer choices, this value is closest to 2.5. Let's trace it. 2.507. And yes, in fact, that is my 0. So I'm going to go ahead and say I agree. That is the place where my function's equal to 0 and changes from negative to positive values. Now remember, I'm not a huge fan of trace unless you're using it on a multiple choice test just to verify that that is in fact the correct answer. Other than that, do not use trace. You need exact decimal places. If they're not given to you on a free response section, you need to find that by yourself. All right, number 6 does not actually need a calculator, so we can put our calculator aside. It says the graph of f prime, the derivative of f, is shown above. This is f prime. The line tangent to the graph of f prime at x equals 0 is vertical. So there's a vertical tangent line right here. All right, cool. F is not differentiable at x equals 2. Yep, there's a cusp there on the graph. And which of the following statements is true? Part A, f prime does not exist at x equals 2. That's not true. F prime does exist at x equals 2. The derivative of this does not exist because it's not differentiable, so the second derivative does not exist at that point. But since this is a graph of f prime, as long as there is a point at 2 on the derivative graph, then the derivative does exist. So yes, the derivative exists, even though the second derivative does not exist. So A is not a true statement. B, f is decreasing on the interval from 2 to 4. So from 2 to 4, they said that f is decreasing. Well, no, because the first derivative is positive. This is a graph of the first derivative, and it is a positive value here in between 2 and 4. So since the first derivative is positive, the original function would have been increasing on this interval. Again, if I was going to correct this to be a true statement, I would have said f prime is decreasing on the interval from 2 to 4. But f is not. F is increasing. Part C, the graph of f has a point of inflection at x equals 2. Well, remember, anytime there's a maximum or a minimum on the derivative graph, that indicates a point of inflection on the original function. So since this is a maximum on the derivative, then yes, on the original function, that would have been a point of inflection. So C is a correct answer. Let's talk about D, make sure that we don't agree with D and E. D says the graph of f has a point of inflection at x equals 0. Nope, that's not a maximum or a minimum, so therefore the point of inflection does not exist there. And E, f has a local maximum at x equals 0. No, this is a local minimum because it's changing from negative values to positive values. That would be a local minimum at x equals 0, not a local maximum. So D and E are out. C is the only answer I agree with. Number 7. Number 7 says, let y equal f of x. Define a twice differentiable function. Let y equal t of x be the line tangent to the graph of f at x equals 2. It says, if t of x is greater than or equal to f of x for all real x, which of the following must be true? All right, this is a very conceptual question, but t of x being greater than f of x means that since t of x is the tangent line, it means that the tangent line is greater than the function, or in other words, that the tangent line is above the function. So I'm actually going to pull up really quick, see if I can bring it over for us. This. I just want to scroll down really quick and direct your attention to this. So remember earlier we said tangent lines lie below a curve versus tangent lines lie above a curve? Well, since concave up shows tangent lines below the curve, and concave down shows tangent lines above the curve, you can see that tangent lines being above or below has to do with the concavity. So because in this example that we're doing, they're telling us that the tangent lines are greater than the function, that would be that the tangent lines are above the function. They're lying above the curve. So for this one, we're looking at a concave down function since the tangent lines are above the curve. T of x is greater than f of x. So this is t of x, and this is f of x. So it's saying which of these has to be true if this is the case. If the tangent lines are above the function, which of these has to be true? Well, since it has to do with concavity, that means the second derivative must be negative since it's concave down. So which of these says second derivative being negative? Well, this is original function. Since this is the original function, this is the first derivative, and these two are talking about the second derivative, and this is the one that says the second derivative is negative because it says the second derivative is less than 0. So that's the true statement. All right, we did those ones. The last one we need to look at is the free response question. So for the y's, if it's okay with you, I'm just going to talk out loud about them. I'm not going to write them down because we've done them many, many times. So I'll just discuss and then we'll write them down. So first of all, it says the figure above shows the graph of f prime, the derivative of the function f. The domain of f is the set of all real numbers such that -3 is less than x is less than 5. So keep in mind this is an open interval, not a closed interval, and that this is the derivative graph. Part A, for what values of x does f have a relative maximum? So we have a maximum at -2. Then we come over here at 1, we bounce, so that's not a maximum or a minimum. And then over here at 4, we cross through, but that's a minimum, so that's not going to be 1. So if I had to answer the y, I would say x equals -2 is a relative maximum because the derivative is equal to 0 and the derivative changes sign from positive to negative. For part B, at what values of x does f have a relative minimum? Well, we just said 4 is a relative minimum. X equals 4 is a relative minimum because the derivative is equal to 0 and changes sign from negative to positive values. For part C, on what intervals is the graph of f concave up? Use the derivative to justify your answer. Well, remember that the original function will be concave up wherever the derivative is increasing. Because remember, concave up indicates increasing slopes. So the derivative is increasing from -1 to positive 1. -1 to positive 1. And then also from 3 to 5. Union 3 to 5. And again, to justify my answer, I would say the first derivative is increasing on those intervals, therefore the original function is concave up. And last but not least, it says for part D, suppose that f of 1 equals 0. So f of 1 equals 0, I'm just going to put a point right there. It says in the xy plane provided, draw a sketch that shows the general shape of the graph of the function f on the open interval from 0 to 2. Well, really they're just looking for a rough sketch of like what's happening. So for example, we know that at -2 there's a maximum, at 4 there's a minimum, but notice that we're not even being asked to graph outside of the interval from 0 to 2. So I really just want to know what's happening between 0 and 2. So because we just care about between 0 and 2, let's come up here really quick. So if you look between 0 and 2, notice that the function is increasing and then changes to decreasing in between 0 and 2, which means that since this is increasing, the original function would have been concave up, and then it changed to decreasing, which means the original function would have been concave down. Now notice that this is a maximum on the first derivative. So since this is a maximum on the first derivative, that means the original function at a point of inflection, which makes sense since the original function was changing from concave up to concave down. Now, because this is a graph of the first derivative, and because in between 0 and 2, the first derivative is always below the x-axis, that means the first derivative is negative. Well, since the first derivative is negative, that means the original function was always decreasing in between 0 and 2. So here it's decreasing concave up, and here it's decreasing concave down. So if I'm going to draw a rough sketch of what that looks like, if I can find my pencil again. If something is decreasing concave up, it might look like this. And if it's decreasing concave down, it might look like this. And I know it goes through the point 1, 0 because it says right here that it goes to the point 1, 0. So anyway, concave up, concave down, always decreasing, looks something like that. And that is the end of our packet, our review packet.